Hi guys, and welcome to this virtual lecture course on the quantum theory of condensed matter physics. I'm Dr. Andrew Mitchell, and in this lecture I want to talk about tight binding models used to describe non-interacting fermion systems. These models can be used to understand the properties of a wide class of materials through their band structures, as well as certain molecular systems, and quantum transport through nanowires and other nano devices. In the last lecture, we talked about the second quantization formulation for quantum many-body systems, and applied it to some simple examples, including the electron gas. In this lecture, I want to talk about the second quantized version of tight binding models, and also the solution of those models, which is basically equivalent to solving the Schrodinger equation. I will discuss how one can construct a many-particle Hamiltonian matrix and diagonalize that matrix to obtain the solutions to tight binding models. But I'll also describe how for tight binding models there is a much simpler way, which involves the canonical transformation of the operators to bring the Hamiltonian operator into diagonal form. We will see that the solutions of such a model can be interpreted as a band structure in momentum space for periodic systems where such canonical transformation is actually just the Fourier transform. Okay, let's get down to work. In this lecture, we'll be discussing tight binding models, which I introduced in the last lecture. This is the most general form of the Hamiltonian, where the sum is over orbitals or lattice sites of the system, labelled I and J. Tij is the tunneling matrix element between those orbitals or sites. Ci dagger creates an electron in orbital site I, and Cj annihilates an electron in orbital J. Also, because of the property of hermeticity of the Hamiltonian, which guarantees that we have real eigenvalues or real energies, we know that H dagger is equal to H, and this actually gives us another condition that Tij must be equal to Tji star. A slightly more conventional way of writing this Hamiltonian might be in the following way, in which we have a sum over sites I with some on-site energy epsilon I, and then we have a number operator for site I. So epsilon I here is a potential energy, if you like, for each orbital I, and the energy of the whole system depends on how many electrons are in each orbital. And of course here the number of electrons, because we're talking about fermions, can just be 0 or 1. So this term here corresponds to a potential energy term, and to this we add a kinetic energy term, which involves the movement of electrons from one site to another. And here we write Tij, Ci dagger Cj, and this term can be thought of as a kinetic energy. Because electrons are moving from one site to the other. So you can see that this Hamiltonian is actually equivalent to the more general form that I wrote down. I'm just writing here that Tii is equal to epsilon I. In this Hamiltonian, I've also introduced a simplification, which is through this sum over I and j with these angle brackets that typically denotes the sum over nearest neighbours. So instead of having every orbital coupled to every other orbital in the system, we assume, for the sake of simplicity, that each orbital only couples to its neighbours. That's physically motivated, of course, because atomic orbitals are exponentially well localized, and the tunneling matrix element for electrons to move from one orbital to the other will be exponentially small if the separation is large. This is not actually an important approximation. We can relax that, and we'll see what happens when we relax that later on. But it's very common and quite conventional in tight binding models to just have to restrict our sum here and just have the sum over nearest neighbours. So this model describes a set of quantum orbitals labelled by I, each with energy epsilon I, and a tunneling matrix element Tij, which describes the movement of an electron from the orbital I to one of its nearest neighbours J. Physically, these tight binding models describe many condensed matter materials seen in solid-state physics, and also many molecular systems. These Hamiltonians are said to be quadratic because we just see pairs of creation and annihilation operators. You have a Ci dagger and a Cj, for example. There are no terms involving 4 fermionic operators. Therefore, these models, as we'll see, represent non-interacting systems. We'll come on to discussing interacting systems with these so-called 4 fermion terms later on in the course. But for now, what kind of systems do these tight binding models describe? Well, for example, we can describe materials where we have atomic orbitals on particular atoms arranged into a lattice so that the atomic orbitals overlap, and so the electrons can tunnel from one orbital to the other, and in a metal, for example, the electrons can actually roam freely over the entire structure. As an example, let's consider a 2D square crystal lattice. This is something that is relevant to the description of high-temperature superconductors, for example, the perovskite yttrium barium copper oxide, which contain 2D square lattice planes of copper oxide. Let's draw a sketch of that arrangement. So first of all, let's consider a 2D square lattice of the atomic nuclei drawn here in blue. And now let's consider the p orbitals of each atom, for example, the px and py orbitals, and the pz orbitals will be pointing out of the page. And we'll ignore those in this analysis. So how does it look when we put these orbitals on each of the lattice sites? So there we have it. The orbitals have the correct symmetry, so that on each lattice site we have orbitals overlapping with each of its nearest neighbours on the square lattice. The electrons can therefore tunnel effectively from one atom to the next on the lattice because of the overlap of the atomic orbitals, and of course this is what a chemical bond is. The reason why the lattice adopts this square lattice structure is precisely because the electrons can form these chemical bonds in this arrangement. The electrons are shared between the atoms and become itinerant, meaning they can move throughout the lattice. So, the overlap between the atomic orbitals means that these atomic orbitals are not well-defined quantum states on their own. Electrons in such atomic orbitals have a finite lifetime, since they can quantum tunnel to a neighbouring site on the crystal lattice. And the amplitude for doing that is precisely the tunneling matrix element Tij, between nearest neighbour sites I and j. The on-site energies epsilon I and epsilon j correspond to the energy of the particular orbital in question, which depends on which atomic orbital we're talking about, and indeed which atom we're talking about. And of course, in the end, this is why different materials with different chemical compositions have different structures, different bonding characteristics, and in the end, different physical properties. And that's what we seek to understand by analysing and solving these tight binding models. Let's have a look at an example of a molecule which can be well described by a tight binding model. Let's consider the famous molecule of benzene, which consists of 6 atoms of carbon in a sort of hexagonal arrangement here. There are also 6 carbons, but I've not drawn those. I've also indicated the double bonds on this molecule. However, actually, that's not the way it really works in nature. This structure that I've drawn is equivalent to this other structure. They're in sort of resonance, if you like, and all of the atoms and all of the bonds are completely equivalent in benzene. It has a perfect 6-fold symmetry. So let's remind ourselves of the chemistry of this system. The carbon atoms have orbitals which hybridize to form this hexagonal structure. This is so-called sp2 hybridization. And that works by hybridizing an s orbital in carbon with the px and py orbitals to form this sp2 hybridized object. And that looks something like this, with the angle between these bonds being exactly 120 degrees. In addition to this, we of course still have the pz orbital, which sticks out of the plane. So it turns out that the molecule is held together essentially by these bonding orbitals, so-called sigma bonds, which make up the backbone of the structure. These are the sp2 hybridized orbitals. And then there are these additional pz orbitals which stick up above and below the plane of the molecule, and they form the so-called pi bonding network, where we have delocalized electrons that can move around. So they are delocalized. Okay, so let's see how this looks. Here in blue, I've again drawn the atomic nuclei, which in this case is carbon, and I've tried to draw it here in perspective. Actually, of course, this is a perfect hexagon. Okay, so now I've drawn on these sp2 hybridized orbitals, which are 120 degrees apart, and you see that they make these nice chemical bonds between the atoms when they're arranged in a hexagon. The orbitals sticking out away from the backbone of the molecule, of course, form the bonds with the hydrogens. Okay, so what about the pz orbitals? They stick out above and below the plane of the molecule. So I've drawn those here in black. And each of these pz orbitals contains a single electron, and the electrons can actually tunnel from one orbital to the other above and below the plane. And I've illustrated that here by the green and the yellow lines. And so this is what we have. The blue dots are the carbon nuclei, the red bonds are the sp2 hybridized carbon atomic orbitals forming the sigma bonding molecular backbone. The black orbitals are the carbon pz orbitals, which each contain one electron and together form the pi bonding network of delocalized electrons. Okay, so what would the Hamiltonian of such a system look like? Okay, so this is the Hamiltonian, which I'm actually just writing for the pi bonding orbitals. So these are the set of 6 pz orbitals that are out of the plane of the molecule. So the sp2 hybridized carbons that are holding the molecule together are just forming chemical bonds, and actually they're a bit boring. So actually here I'm just writing a Hamiltonian for the electrons that can move around, which are the pi electrons. And so what I have here in the first term is a sum over the 6 sites of the system, 1 to 6, and because there is a symmetry of this molecule between all of the 6 sites, they have a common energy level, epsilon. And then I just have the number operator counting the number of electrons in that site. The second term is a kinetic energy term, and I have a tunneling amplitude T that connects nearest neighbours. And so you see here I have a term in the Hamiltonian that destroys an electron on the I plus 1th site and creates it in the ith site. And I do that for each pair of sites on the ring. Notice also that I have 2 terms in here. For every electron that I hop from I plus 1 to I can also hop from I to I plus 1. So each of these terms separately is not Hermitian, but they are Hermitian conjugates of each other, so that if I had to take H dagger, the terms would just turn into each other, and overall H dagger would be equal to H. So one other small note here is that I have a sum from 1 to 6 over the 6 sites of the system, but in this Hamiltonian I have an index I plus 1, so here I'm assuming that site I equals 7 is actually back to site 1 again. So that's the cyclic nature of having a ring here. Good, so that's it. If we were to solve this model, we would find out what the molecular orbitals were. They would be the eigenvectors of the Schrodinger equation, basically the wave functions, and we'd be able to find out the energies of the electrons in this system as well. That's to come later in this lecture. Okay, so let's go back to a lattice system. In fact, let's consider a very famous example of graphene, which is a 2D hexagonal lattice of carbon atoms. And in fact, we could construct the graphene lattice from the benzene molecules that we were just talking about. We can consider each hexagon in the 2D plane of graphene as like a benzene ring. They're all just coupled together in the following way. Imagine first that we have our 6 carbon atoms of a single benzene ring, and now we add on our sp2 hybridized bonds to form the bonding network, and then we simply repeat this unit to tile the 2D plane as a hexagonal lattice. Here are the carbon atoms of the lattice, and here are all the p orbitals laid on top. And of course, this is supposed to be a periodic system, so we can imagine repeating these hexagonal units throughout the two-dimensional plane of the graphene sheet. So the graphene structure is actually held together by these sigma bonds, which are made up from sp2 hybridized carbon orbitals on each atom, but these orbitals overlap on the lattice. Each carbon atom contributes 1 electron per sp2 hybridized orbital, and therefore each chemical bond has 2 electrons in it, 1 contributed from each of the atoms, and these chemical bonds are therefore very stable. The entire hexagonal 2D lattice structure of graphene is extremely stable. However, we've not yet considered the pz orbitals that stick above and below the plane, and these form the pi bonding network that I want to discuss in more detail. So here I've drawn, again, the backbone structure of the sigma bonds, but this time just in a simplified notation denoting this hexagonal lattice. Now let's draw on top of this the pz orbital sticking above and below the plane. Okay, so here are all of the pz orbitals drawn in, and as you can see, they form a pi bonding network that is also a hexagonal lattice, and I've drawn this in green. I've just drawn it above the plane. Notice also, however, that the pz orbitals overlap below the plane as well. Each carbon atom contributes a single electron to this pz orbital, which points above and below the plane, making up the pi bonding network. And this is the thing that we typically model in the condensed matter treatment of the hexagonal lattice. So let's have a look at the Hamiltonian for this pi bonded network in graphene. Here it is. It's in the usual tight binding form. The first term, we have the potential energy, which tells us the total energy of the system has a contribution from the individual energies of the particles in individual orbitals. Those orbitals are all equivalent by translational symmetry on the lattice. We give them an energy epsilon, and then the total energy just depends on how many electrons are occupying those orbitals. The second term is a kinetic energy term, where we allow for the electrons to tunnel from one orbital to the next. And here I have explicitly written the sum as the sum over nearest neighbours on the hexagonal lattice. So we can successfully formulate these tight binding models for various physical systems of interest to us. The question now is how to actually solve these models, and that's what we'll be coming onto next in this lecture. So the next major topic is how to actually solve these tight binding models. In fact, what I'll say will apply completely generally to any non-interacting fermion system. There are two basic ways we can consider doing this. There's like a brute force approach, where we construct in many particle basis the Hamiltonian matrix and then diagonalize the matrix. And the second method involves performing a canonical transformation of the operators in the Hamiltonian to bring the Hamiltonian operator to diagonal form. For non-interacting systems, this second approach is definitely the most efficient and best approach. However, I want to start with the many-particle version first, as this is the most basic and foundational way of solving such models, and indeed this will also prove to be very important when we consider interactions later on in the course. So, this first part will be on constructing and diagonalizing the Hamiltonian matrix in the many-particle basis. So first of all, let's be precise about what we mean by a basis, and in particular what we mean by a many-particle basis. Importantly, we need a complete basis, meaning that every possible state of the system can be described as a superposition of these basis states. One convenient and obvious choice is that basis states should be the occupation number product states that we talked about in the last lecture. Remember that these are kind of like classical basis states, which involve the direct product of the vector spaces for the individual constituent orbitals of the system. For example, let's consider a two-orbital system. In occupation number language, we can define basis states like this. This one means that there's no electrons in either of the two orbitals. We have one electron, which can either be in the first orbital or the second one, or we can have two orbitals. So this complete orthonormal basis must span the entire Fock space of the system. And since this is a complete orthonormal basis, we can write an identity operator which is the sum of projectors onto all of these basis states. So here we have a sum over all basis states, and the basis states lambda are it's a shorthand for these occupation number basis states. So let's say I have some arbitrary state psi, which could be, for example, the eigenstate of some Hamiltonian. I'm not saying this is a product state or a basis state, this is just some arbitrary state. This state psi is obviously equal to the identity operator acting on the state psi. That's what the identity operator is. It basically just multiplies it by 1. However, it does allow us to resolve this state in the basis in which the identity operator is written, because if I just write out what this identity operator is, we see that it's projectors onto the basis state, the basis states lambda, and then I have the state psi being acted on with all of this lot. And here we see that we have the inner product of the ket of psi and the bra of lambda, and this is some number, and I'm going to call that number u, and I'm going to parameterize it by the index lambda for the particular basis state we're talking about, and also psi to keep track of the state that we're investigating. So this whole thing, therefore, is equal to the sum
over lambda of some numbers which are essentially expansion coefficients times some basis states lambda. And so this is an important equation because it tells us that we can write any state psi in the basis of our occupation number states. And in particular, you'll notice that some arbitrary state psi is a linear combination of basis states. So it is not necessarily itself a product state, but we can express it as the superposition of product states. But actually there's more, because we can change basis from one basis to another. How do we do that? Well, consider that we have the identity operator resolved in some other basis. So this is still the identity operator, but I'm writing it in a different basis. Let's say the basis of phi, where I now have projectors onto different basis states, phi, and these can be anything, provided it's a complete orthonormal basis. And by exactly the same logic, this allows us to write that our arbitrary state psi is equal to the sum over phi of u phi psi of the basis states phi ket. So we can write our arbitrary state psi in any basis we like, so long as we know what this identity operator is in a given basis. That basically means have we identified what all of the basis states are that span our complete Fock space, and once we know those states, we can write down the identity operator, and once we know the identity operator, we can act with it on an arbitrary state to resolve it in that basis. So what are the general properties of such a basis transformation? Well, we have in our original basis the following facts. One is that it must be complete, meaning that we have a resolution of the identity. And also, it should be orthonormal, meaning that we can take the inner product of lambda I and lambda j, and this should be equal to the delta function, the Kronecker delta, delta ij. We can actually write that in a slightly more compact way, as we discussed in the first part of the course for spin systems. Let's suppose that we write down a vector, which I'll call lambda vector. Actually, this is like a row matrix. That's the right way to think about it. And this is just basically a vector of all of the different states of the system, and the kets. So lambda 1, lambda 2, lambda 3, and so on. We can write the completeness condition, therefore, in the following compact way. So if I form this product, this is basically a matrix product of lambda and lambda dagger, then indeed I get the scalar sum of all of these projectors. Also, I can write the orthonormality condition by writing that the identity matrix is equal to lambda dagger times lambda. Lambda dagger times lambda gives me an n by n matrix if I have n basis states, and that matrix will be the identity matrix, meaning that elements of it are equal to delta ij if we have an orthonormal basis. So this is a nice compact way of describing our original basis. If we perform a basis transformation to some other basis, we have to ensure that this new basis is also complete and orthonormal. Let's enumerate the basis states of this new basis in a vector phi, which just means the ket phi1, the ket phi2, and so on, assembled into one giant vector, or again, as I've written it here, actually a row matrix. Let's take a given state of this basis, let's say phi I, and express it in terms of the original basis. We just do exactly what we did on the previous slide. We use the resolution of the identity in the original basis, and we act on our state phi I with this operator to obtain the following. I sum over all of the basis states lambda j of the original basis, and then I act on that with our state, onto our state phi I. And then, as before, I just recognize this inner product here of the ket phi I with the bra lambda j to be u j I. It's some number, it could be a complex number. And so overall, we just have the sum upon j of u j I times the basis states of our original basis, lambda j. So we have a linear superposition of those states. Okay, so that's all fine. However, this same argument applies for any of our states phi I in the new basis, and so I can actually assemble all of that information in a compact way in the following. I can write in terms of our phi and lambda vectors that our phi vector is equal to a U matrix times our lambda vector. So this is a very important equation defining a basis transformation. And elements of this matrix U are exactly these U, I, J numbers that we were talking about previously. So how can we guarantee that our new basis is complete and orthonormal? Let me just write out again our basis transformation equation. For our phi basis to be complete, we require that phi dagger is equal to the identity operator. However, we can write this in terms of our original basis using our matrix transformation equation, which would tell us that we can write phi dagger in terms of our lambda and our u expressions, remembering here that the dagger means the conjugate transpose. And this object inside here is the definition of the completeness of our original basis. So if we assume that our original basis is complete, then this is the identity operator. And since the identity operator is a scalar quantity, we can move it through the matrices and obtain this. So what we've learnt is that for the phi basis to be complete, we require that U dagger is equal to the unit matrix, and that means that this matrix U is unitary. And a unitary matrix is one where U dagger equals the identity, or put it another way, the inverse matrix is equal to the conjugate transpose. Good. Okay, so we've learnt something about what kind of transformations are good transformations, good meaning that our new basis is complete. What about orthonormality? This is where we want that phi dagger phi is equal to the identity matrix. But we can play the same game and write this in terms of our lambda and U matrices to obtain the following. And we've just learnt that we want U dagger to equal the identity. That also implies that U dagger U is equal to the identity. And so if this is equal to the identity matrix, then overall, that drops out. And we obtain this, which we know from the original basis is equal to the identity. So indeed, if U is unitary, then we also guarantee the orthonormality. So the only kind of transformations we're interested in are unitary transformations. These are basis transformations which preserve the completeness and orthonormality of the original basis. Okay, so you might be wondering what all of this has to do with solving tight binding models. Well, as we'll see, solving the Schrodinger equation is essentially equivalent to doing a basis transformation from our original basis to the eigenbasis of the Hamiltonian. That is a basis where the Hamiltonian becomes diagonal. But how do we actually find this correct eigenbasis for a given Hamiltonian? What is the transformation U, and what information does that matrix contain? That's the next topic. First of all, we need to construct the Hamiltonian matrix. The Hamiltonian matrix is obtained from the Hamiltonian operator, H hat, by sandwiching it between our basis states. So let's imagine that we start off in our original occupation number product state basis, which I've been calling phi. We have this vector phi, which define our different basis states. And please notice that these basis states are in the many-particle basis. What do I mean by that? I mean that we fully enumerate all of the states in the system. N1 in 1, an occupation number N2 in orbital 2, an occupation number N3 in orbital 3, and so on. So this is fully enumerating everything that's going on in the full system in terms of the occupation numbers. And the shorthand for all of that stuff is just a given basis state, which I'll call phi 1, phi 2, phi 3, and so on. All possible many-particle basis states are assembled into this vector, which is the phi vector. Okay, we have some Hamiltonian operator, H hat, and I can construct a Hamiltonian matrix, which I'll denote with the double lines underneath for a matrix, simply by taking phi vector dagger, H hat for the Hamiltonian operator, and then phi vector. How does that work? Well, we can just imagine writing this out. We have phi 1, phi 2, phi 3, and so on in a big column matrix for the phi vector dagger. Then we have the Hamiltonian operator, h hat, and then I have phi vector, which are again just these basis states, but this time the kets. So you can see that how this works. First of all, I act on my state phi 1 with the Hamiltonian operator and see what that gives me. Then I consider the overlap of that object with the phi 1 bra, and then I consider the overlap of that with phi 2 and phi 3, and so on. And this gives me a whole vector or column matrix for h acting on phi 1 and the overlap with all of the original basis states. And then I do the same thing for h acting on phi 2, and then I consider the overlap with the original basis states, and so on and so forth. And so this gives me the following important relations, that if I consider an element ij of this Hamiltonian matrix, that is equal to phi I h phi j. This is a matrix element. I first act with h on phi j, then I consider the overlap with phi I, and that is a matrix element hij. And here we're doing this explicitly in the phi basis. If this seems a bit cryptic, let's do an example of the simplest non-trivial system of two orbitals. We can write down all of the possible basis states of two orbitals in our phi vector, and you've seen it many times already now. I'm just going to enumerate the basis in the occupation number basis, like so. That's it. And let's consider a specific Hamiltonian operator. Let's say that we have two orbitals, each with energy epsilon. So I have epsilon times C1 dagger C1 plus C2 dagger C2. They both have the same on-site energy. But we also allow for a tunneling of electrons from C1 to C2 and back again from C2 to C1. And of course I have to include both of those two terms for hermiticity. Okay, so let's construct the Hamiltonian matrix now and see what we get. The Hamiltonian matrix H is equal to phi dagger H hat phi. And in particular, we can work out the matrix elements. We've done something similar to this before, so let me just go through this quite quickly. Let's imagine first that we have H acting on our state 0, 0. This just gives us 0. Imagine that we have H acting on 0, 1. This gives us epsilon times 0, 1. An on-site energy of epsilon for site number 2 because there's an electron there. But also, the tunneling term converts the 0, 1 into the 1, 0. This, of course, then implies that if I take 0, 1, H 0, 1, I just pick up epsilon, whereas if I take 1, 0, H 0, 1, then I pick up a factor of t. So this is very straightforward. Similarly, with H acting on 1, 0, I get epsilon of 1, 0 back again, plus t of 0, 1. The Hamiltonian converts the 1, 0 into a 0, 1. So likewise, I can form matrix elements. Good. What about our final equation? I have H acting on 1, 1. This just gives me 2 epsilon of our state 1, 1 back again. And that, of course, only has overlap with itself. So we can assemble all of this information into the actual Hamiltonian matrix now. And that Hamiltonian matrix looks like this. The Hamiltonian matrix is a 4x4 matrix. And the easiest way to visualize it is to just enumerate the bases along the top. And on the sides, and then you can easily see what the matrix elements are that we're talking about. So, for example, we saw earlier that the matrix element of H with 0, 0 to 0, 0 just gave us 0. The other diagonal elements, 0, 1 to 0, 1, gave us epsilon. 1, 0 to 1, 0 gave us epsilon, whereas 1, 1 to 1, 1 gave us 2 epsilon. You can see that these diagonal elements are basically giving us the energies of these basis states in the absence of any quantum tunneling. But then we can consider the effect of the quantum tunneling of the electron from the first orbital to the second orbital, and we see that those elements go here and here. Everything else in this matrix is equal to 0. And in fact, we can see that this matrix has a block diagonal structure. The only elements that are non-zero lie within these diagonal blocks, and in fact, the only non-trivial block is this 2x2 block sitting in the middle, which connects the 0, 1 to 1, 0 states. An obvious question is, why does the Hamiltonian have this block diagonal structure? The reason is that the total electron number in this Hamiltonian is conserved. So let's write down number operator n hat is n1 plus n2. It's the total number of electrons. We see that the Hamiltonian commutes with this operator, meaning that total number of electrons is conserved. What do I mean by the total number of electrons is conserved? Acting on a state with a definite number of electrons, n, with the Hamiltonian, does not change that number of electrons. So let's label our basis states according to this quantum number. Of course, we see that this block is n equals 1, this block is equal to n equals 0, and this block is n equals 2, and likewise on the top. This is n equals 0, this is n equals 1, this is n equals 2. So the Hamiltonian cannot change this n because n is conserved. So that tells us that there are no matrix elements in this Hamiltonian that connects, for example, the n equals 0 and n equals 1 subspaces. That would be these terms. Or n equals 0 and n equals 2. That would be this term. Likewise, there are no elements connecting n equals 0 and n equals 1, which is this block, or n equals 0 and n equals 2, which is this block, or n equals 2 and n equals 1, and so on. So we have a block diagonal structure. Indeed, because there's only one state with n equals 0, that's a unique state, and so the basis state must be the eigenstate. Likewise for n equals 2. However, for n equals 1, there are two states, and they can get mixed up under application of the Hamiltonian, and that's what we see explicitly. The block diagonal structure of the Hamiltonian is very important because it means that we can diagonalize the Hamiltonian separately in each of these conserved quantum number blocks. In particular, we can write down sub-Hamiltonians in each of the quantum number blocks. So we can write down the Hamiltonian in the n equals 1 sector. We have H, let me denote the Hamiltonian matrix H of n equals 1, so we can be clear about what we mean. That's now a 2 by 2 matrix, which is of course much simpler to deal with, where this matrix is comprised of the 0, 1, 1, 0, and 0, 1, 1, 0 states. That's what we mean by this sector. Of course, I also have the n equals 0 sector, where H of n equals 0 is actually just a 1 by 1 matrix, or a scalar. That's just 0, quite boring. Also, we have the n equals 2 sector, H n equals 2. That's also a 1 by 1 matrix, or a scalar, marginally less boring, but still just equal to 2 epsilon. So, we see that the 0, 0 and the 1, 1 states are eigenstates of the Hamiltonian, but that the 0, 1 and 1, 0 states are not eigenstates of the Hamiltonian. They get mixed up. So, we want to solve the Schrodinger equation Let's do this for our two-orbital system. Solving the Schrodinger equation means that we apply the Hamiltonian operator to a given eigenstate psi I. We get the state psi I back again, multiplied by its corresponding eigenvalue, which is the energy EI. Now, let's try to solve the Schrodinger equation for all possible eigenstates in one go using our matrix representation. Let's suppose that we have a vector of eigenstates, which I'm going to call psi vector, which is precisely the usual row matrix psi 1, psi 2, psi 3, and so on. For the two-orbital system, we have 4 eigenstates. Fine. Okay, so let's imagine that we apply the Schrodinger equation to each individual element of that vector. We can assemble all of that information in one equation by writing that H operator acts on psi vector, and that's going to give me the psi vector back again, that's what we want, multiplied by a matrix D. And this matrix D is a diagonal matrix. That's why I called it D. And what I mean by a diagonal matrix is that elements of D are proportional to the Kronecker delta, meaning that you only have non-zero entries running along the diagonal. And in particular, those entries that are non-zero, so the ith element of D, is exactly equal to the eigenenergy EI that we had from the original Schrodinger equation. Okay, so this is exactly equivalent to the Schrodinger equation, but this time for all of the eigenstates in the system, just written in one single equation. Okay, we can actually go further, which is to utilize the fact of the orthonormality of the basis, which tells us that if I write so if I were to write psi dagger times psi, then I know this is equal to the identity matrix. So I can utilize this expression to further write our Schrodinger equation by pre-multiplying by psi dagger. So I pre-multiply the whole equation, left and right sides, by psi dagger. And because D is a diagonal matrix, the right-hand side is simply equal to D. And that's because we have the orthonormality of the eigenstates psi dagger psi is equal to identity. And on the left-hand side, we actually have the definition of the Hamiltonian matrix. So what we see is that in the eigenbasis, and let me label the Hamiltonian matrix here according to the basis in which we're calculating it, so H psi is actually equal to this diagonal matrix D, which is just a matrix of the eigenenergies on the diagonal. Just one clarifying point here. On the left-hand side, we have the Hamiltonian matrix in the eigenbasis. That's why I've labelled it with this subscript psi. The Hamiltonian matrix looks different in different bases. Okay, so that's what we mean by solving a Schrodinger equation. We want the Hamiltonian matrix to be a diagonal matrix of eigenvalues. But the problem, of course, is that we don't know the Hamiltonian matrix in the eigenbasis. We only know the Hamiltonian matrix, so far, in the original product state occupation number basis. So what we want to know is the transformation, which is basically a change of basis between the original occupation number basis and our eigenstate basis. So this equation that I've written down is exactly what we had before. It's a change of basis. We're changing from the original occupation number basis, let's say product state basis, to the eigenbasis. And this U here is a unitary matrix. And of course this makes eminent good sense because we know that the eigenstates are a superposition or linear combination of the original classical-like product state basis states, and that's encoded in this matrix equation. Okay, we still don't know what the unitary matrix is, but we do now have a condition. So we will write that psi dagger H psi, which is on the left-hand side of our Schrodinger equation here, using this transformation property, the change of basis, is equal to U dagger phi vector dagger H phi vector U matrix. Remembering again that the dagger means the conjugate transpose. And we recognize in this expression this middle thing as being the Hamiltonian matrix, but this time in the original basis, phi. And we do know the Hamiltonian in the original basis, phi. That's the thing that we were at pains to calculate on the last slide. And so in this expression, we have the following. Namely, and this is the ultimate expression that we're looking for, that the Hamiltonian in the eigenbasis, Hamiltonian matrix in the eigenbasis, H psi, is equal to U dagger H phi U. And this whole thing, as we know, of course, is equal to a diagonal matrix, D. So this is the central equation that we're looking for. It tells us that we can construct a Hamiltonian in our original basis, our easy product state basis, and we can relate that to the Hamiltonian in a different basis, the eigenbasis, which is actually a diagonal matrix. And how do we do that? By performing this matrix product U dagger H U. And this thing is referred to in the mathematics literature as a similarity transformation. It's a similarity transformation when we're using this matrix U, which is unitary, and it's similar in the technical sense because the transformation preserves the determinant of H phi and the trace of H phi. So that's the sense in which H phi and H psi are similar. And this is precisely just the usual procedure of diagonalizing a matrix. So if we have a 2x2 matrix for the n equals 1 block, we can do this by hand using the usual techniques you learnt at high school. However, in a more general case, diagonalizing this matrix requires to be done on the computer, so we just write in our Hamiltonian matrix in the original basis and diagonalize it, and that will produce our diagonal matrix D. The diagonal entries of that matrix are precisely the eigenvalues of the original matrix, which are the energies of our states. And, importantly, if we look at our transformation matrix equation here, we see that a given psi I can be written in terms of a superposition or a linear combination of our product state basis. What I mean by that, just to write it out very clearly, is that a given psi I, I'll write it down here, is equal to the sum over j of u ij times our phi j states. Okay, and that information about the wave functions, the expansion of a given eigenstate in the original basis, is precisely the elements uij. So the columns of our matrix U are the wave functions that we're looking for. They're the expansion of the eigenstates in the original basis. Okay, so that might have seemed somewhat abstract, so let's do an actual calculation. Let's consider the two-orbital system as before, and in particular, let's consider the n equals 1 sector. Now, I already explained that the Hamiltonian matrix in the product state basis is block diagonal. It's block diagonal because we have conserved total particle number, and we can look at the total particle number 1, and we can see what's going on there. We have a Hamiltonian matrix in our original phi basis. Let me denote this as being in the n equals 1 sector explicitly. We already worked this out. It's epsilon t t epsilon. It's a 2x2 matrix because there are two basis states in the n equals 1 sector. And the phi here denotes that we're talking about the original product state basis. What we want is to find a matrix U such that U dagger H phi in the n equals 1 sector is times U is a diagonal matrix D. That's the mathematical problem. So I would leave it to you to try to diagonalize this yourself. It's a rather simple one. Let me just tell you the answer. This matrix U is actually the following matrix, 1 over root 2 of 1, 1, 1, minus 1. It's a rather simple matrix. And let's see that that actually works. I need to take the conjugate transpose of this matrix to find U dagger. Actually, it turns out that's the same as U. So U dagger H phi in n equals 1 sector times U is equal to overall 1/2 of 1, 1, 1 minus 1 times epsilon t t epsilon times matrix 1, 1, 1 minus 1. So it's a bit of matrix algebra for us to do. So let's do the product of these first two matrices first. What do we get? Well, I still have the overall factor of 1/2, and then I have to multiply out those two matrices, and I get the following. Actually, it's epsilon plus t, epsilon plus t, and then on the second row, I get epsilon minus t, and t minus epsilon. Okay, and I still have to multiply this by this last matrix here. Let's not forget that one. 1, 1, 1, minus 1. So I still need to do another matrix product of these two things. And when we do that, we see that indeed, magically, we do get our diagonal matrix. It's epsilon plus t in the top left-hand corner and epsilon minus t on the bottom right-hand corner and zeros on the off-diagonal elements. So this is exactly what we want. And the the columns of our U matrix are precisely our eigenvectors. So I can just extract this information and say that I have an eigenstate psi 1 in the n equals 1 sector, and that's going to be the sum over I from 1 to 2 of U 1I of our basis states phi I in our n equals 1 sector. And these basis states are the 0, 1, and 1, 0 states, so that just gives me 1 over root 2 of 0, 1 plus 1, 0. And likewise, our psi 2 in the n equals 1 sector is again the sum over I, but this time of U 2I on the basis states phi I in the n equals 1 sector, which just gives me the combination 0, 1 minus 1, 0. Good. And we know from this expression that when I act with the Hamiltonian on this state psi, let's say psi 1, I get the state psi 1 back again, multiplied by the eigenenergy, and the eigenenergy is precisely this entry in the diagonal matrix corresponding to that first eigenstate, which is epsilon plus t. We also have that when H acts on psi 2 in the n equals 1 sector, we get the state psi 2 back again, but with eigenenergy this time epsilon minus t. Okay, and you can check for yourselves that actually these two linear combinations do indeed satisfy the Schrodinger equation, and they do indeed give these eigenvalues. That's an exercise for you to try yourselves. So let's summarize what we've found. First of all, you need to enumerate our basis of many particle states. And we do this in the occupation number product state basis. And with this information, we construct this vector of basis states, phi 1, phi 2, phi 3, and so on, for all of our basis states. Secondly, we construct the Hamiltonian matrix in this basis. And that is given by h of phi is exactly phi dagger h operator phi, such that an element of this matrix ij is exactly phi I h phi j, so no mystery there. Thirdly, we need to diagonalize this matrix. And what we mean by that is we need to find the unitary matrix U such that U dagger H phi U is equal to a diagonal matrix. And the solution of our Schrodinger equation, therefore, is that we have eigenstates psi I, which are linear combinations of our basis states, superpositions of our basis states, where these uij's are exactly the elements of our transformation matrix U. So these are really expansion coefficients of our eigenstates in the original basis, with eigenenergies, associated eigenenergies EI, which are the diagonal entries of our matrix D. And that's it. That's to solve the Schrodinger equation for a many-particle quantum system using the diagonalization of the many-particle Hamiltonian matrix. This comes with certain advantages and certain disadvantages. So first of all, let me summarize the advantages. One of the advantages, most important advantage, is this is totally general. This really works for any system. In particular, it can be generalized to interacting systems. In fact, you don't really need to do any generalization, it just works for interacting systems. And I would say a third advantage of this is that we obtain eigenstates that are already in the many-particle basis. So that all seems great. What are the disadvantages? There is a major disadvantage with this method, which is that we need to construct the Hamiltonian matrix in the many-particle basis, and that matrix is exponentially large in the system size. What do I mean by that? I mean that the dimension of the matrix is 2 to the n by 2 to the n for n orbitals. So if you're looking at even moderately sized systems, you very quickly run into this exponential scaling of the Hilbert space, or the Fock space as it actually is. And this means that basically large systems are completely unsolvable using this method. Let's say I had 10 sites in my system. I would have a matrix of 2 to the 10 by 2 to the 10. That's a very large matrix that you'd have to diagonalize on a computer, but it's just about doable. But even if I extend this to 100 sites, there's no available computational methods that could solve such a massive matrix, so we're completely stuffed already. Another disadvantage, I would say, is that it's not completely physically obvious what the interpretation of the eigenstates is. It's really a numerical method. We get a numerical solution. As we will see, there are other analytical methods which might reveal some more interesting aspects of the physics of the problem. For example, in a periodic system, we'll see that the solutions are related in some way to what's going on in momentum space. So that kind of information you wouldn't easily see from the direct brute force diagonalization that I've sketched so far. So I'll just say here that another disadvantage of this setup is that the physical content of the solutions is not completely obvious. So now I want to talk about the second approach, which for these kind of quadratic non-interacting systems is far superior. It's a canonical transformation of the fermionic operators which brings our Hamiltonian operator to diagonal form. So we do not construct explicitly the Hamiltonian matrix in the many-particle basis here. We actually diagonalize the operator itself. What do I mean by diagonalizing the operator? I mean that we bring the Hamiltonian into the form of a free electron gas. Okay, so all of this will become a bit more obvious when I start to explain. The first thing we need to do is understand what is a canonical transformation. A canonical transformation is one which preserves the anti-commutation relations of the original fermionic operators. So let's say that we have a set of operators which I'll label as usual by the CIs. So I have Ci and I have Ci dagger. We have commutation relations, which are that the anti-commutator of Ci with Cj dagger is equal to delta Ij. We have that the anti-commutator of Ci with Cj is the same as the anti-commutator of Ci dagger with Cj dagger, which is equal to 0. That's it. That's all we need to write down to understand the algebra of these fermionic operators. And what we want to do is to do a transformation of these operators which preserves these anti-commutation relations. We'll only be interested in canonical transformations. You can imagine doing some arbitrary transformation of operators that wasn't canonical, such that the anti-commutation relations of the new operators were not preserved. But we're not interested in any such transformations. The kind of models we could write down or the manipulations that we could do would not be fermionic in nature, and it would be hard to understand what was going on with such a transformation. So we're only interested in canonical transformations in what follows. So let's suppose that we make a transformation, a linear transformation of operators, let's call them Fk operators, which are going to be a linear combination of our original C operators. And again, I've got some numbers here which could be complex, which are the UKIs, which tell us for fermionic operator Fk, we have to expand this in terms of the Ci's. So these are complex expansion coefficients. I'm calling these U again, and again that's probably telling from our previous discussion that these will end up being unitary matrices or elements of unitary matrices in what follows. However, please note right from the beginning that these matrices U are nothing to do with the matrices that we considered in the previous section. They're actually of a totally different dimensionality, for one thing, and they're really physically different things, but they are unitary matrices in the end, as we'll see, and so I will stick with the notation of calling them U in what follows. So we have these fermionic operators here. I want these to be fermionic. And the fact that I want them to be fermionic places some constrictions upon what these expansion coefficients U, K, I can be. I've already given the game away, they're going to have to be unitary. But let's see why that's the case. For these to be fermionic, I want them to satisfy their own commutation relations. Meaning, I want Fk, the anti-commutator of Fk with Fk primed, let's call it, dagger, to be delta K, K primed. I want the anti-commutator of Fk with Fk primed to be the same as the anti-commutator of Fk dagger with Fk primed dagger, which is to say equal to 0. So I want the same kinds of commutation relations for the F's as I have for the C's. So let's evaluate these anti-commutators and see what happens. Well, it's easy because we've got an expression which relates the F to the C's. I'm supposing that they're a linear combination of those things. So I can just substitute that in. And when I do that, I get the double sum over I and j, because I have two sets of operators, Fk and Fk primed, of Uki times Uk primed j star, star meaning, of course, the complex conjugate as usual, times the anti-commutator of the C operators, Ci and Cj dagger. That's what you get just by substituting it in. And of course, we know that the original fermionic operators are fermionic, meaning that their anticommutator satisfies delta ij. And that has an effect on the double sum. And what we end up with is the sum over simply I of UKI, UK primed I star. And this whole thing should be equal to delta K primed, because I want the anticommutator of Fk and Fk primed dagger to equal delta K primed. And so I've derived a condition upon the expansion coefficients. In particular, we can see that a U matrix with elements I, j is equal to U, I, j. That matrix U is unitary. This property that I've written in the box here is the defining feature of a unitary matrix. And so again, we see that these unitary transformations play an important role in fermionic quantum condensed matter physics. We see that canonical transformations are ones involving a unitary transformation of the operators. And so we can imagine doing a transformation not just of Fk in terms of the Ci's, but doing a transformation of all of the operators in one go. So let's make a vector of operators, C vector, which is just C1, C2, C3, and so on, all the way up to Cn, for an n particle system. I'm writing this as a column matrix. And we can do something similar for the F operators. Let's write an F operator vector, which involves the F operators, F1, F2, F3, and so on, all the way up to Fn. There is the same number of F operators as C operators, obviously. So a canonical transformation connects these two things . It is one in which we write that F vector is U times C vector, noting that the F and the C's are vectors of operators. And U here is our unitary matrix. And just to emphasize, this can be any unitary matrix. Any unitary matrix will constitute a canonical transformation. This matrix is an n by n matrix. You can see that from the dimensionality of these vectors. If I have n orbitals in my system, I will have an n by n matrix U. Now you can already see that this is quite different from diagonalizing the Hamiltonian matrix in the many-particle basis that we talked about in the first half of the lecture, because here we have an n by n matrix of transformation, whereas before we had a 2 to the n by 2 to the n matrix, which is exponentially larger in the system size. So we can already see that this is going to be a more efficient treatment if we can somehow utilize this canonical transformation to solve the Schrodinger equation, which is of course what we want in the end. So the question is, how can we utilize this idea, this concept of the canonical transformation of operators, how can we utilize this to actually do the work of solving our Schrodinger equation? As we'll see, not all Hamiltonians can actually be solved in this way. In fact, it's only these quadratic Hamiltonians that only involve pairs of operators that can be solved using a canonical transformation. But tight binding models, which we motivated at the first half of the lecture, are a good example of the kinds of systems that can actually be solved using this method. Okay, so how does it work? Okay, so this is the type binding model that we looked at previously. We see that we have an on-site potential on each of the orbitals I, and we also have a tunneling matrix element between I and J, where I is not equal to J in the sum here. Also, for reasons of hermeticity of the Hamiltonian, we have to have the condition that Tij is equal to the complex conjugate of Tji. So using this vector notation of the C operators that I had before, it turns out that I can write this Hamiltonian in a rather nice, compact way. I can write this simply in a matrix notation as C vector dagger times some matrix which I'll call T times the C vector. And that's it. Let me just remind you, the C vector is a column matrix of the operators C1, C2, C3, and so on, up to Cn. And a matrix T, which contains all of the coefficients in the Hamiltonian. So the diagonal elements are exactly epsilon 1, epsilon 2, epsilon 3, and so on, all the way down to epsilon n. And the off-diagonal elements are the t's, t12, t21, t13, t31, and so on and so forth. So this one goes up to t1n, this one goes down to tn1, and so on and so forth. And an important feature of this matrix is that this matrix is, of course, an n by n matrix of the coefficients that appear in the Hamiltonian epsilon I and Tij. And you can see that if I multiply this out, C vector dagger T C vector, I get a scalar quantity, which is precisely the Hamiltonian operator that we started with. So the real question we're interested in is how to solve this model, how to bring this to diagonal form. Well, I can utilize our transformation, our canonical transformation of operators. We let the C vector operator, vector of operators, equal a linear combination of F operators, which is contained by this matrix equation, where U, as usual, is unitary. So, if I just plug that into the Hamiltonian, I find that the H operator is equal to F dagger U dagger T U times F vector. And we want this to be something in diagonal form. We want this to be F dagger D. F. D is a diagonal matrix, so let's consider the k''th element of this should be proportional to the Kronecker delta, delta kk primed, with those entries, those diagonal entries, so the k'th element being what we'd call a single particle energy epsilon k. So, we can write our Hamiltonian operator in the form of the free electron gas with single particle energies epsilon k and operators fk. And we can write it in this fashion because our matrix D is diagonal. And to arrive at this form, what we need to find is the unitary matrix U such that U dagger T U is diagonal. So this is very, very similar kind of mathematical structure to the problem that we were talking about in the first part of the lecture, where we need to find a unitary matrix that diagonalizes a particular matrix. In the first part of the lecture, the matrix to be diagonalized was the Hamiltonian matrix in the many-particle basis. Here, the situation is different. The matrix we're trying to diagonalize is a matrix of coefficients that enter the Hamiltonian. The Hamiltonian matrix in the many-particle basis is 2 to the n by 2 to the n in size, whereas the matrix here, T, is just n by n, so there's a drastic difference in the complexity of these eigenvalue problems to actually solve. Actually, it turns out that there is a connection between the two approaches, because the matrix T that we've talked about here is actually the many-particle Hamiltonian matrix in the single particle sector. Also, we can write that eigenstates with a single electron, n equals 1, we can call by these kets k, are exactly these fk operators acting on our vacuum. So these are the quasiparticles of our system. So the quasiparticle means here it's a superposition of the single particle states in the real space basis, meaning that I can expand it in terms of these coefficients. So we can understand something about the single particle states from these operators fk directly. So what we've achieved here is to change the form of the model that we're looking at. We start from some real space model. Let's draw it in cartoons as a bunch of sites. For example, let's look at the 2D square lattice, something like this. So we have something in real space which involves the coupling of these orbitals. They have on-site energies and coupling coefficients between them. And then we diagonalize the Hamiltonian to give a new representation with just a bunch of new orbitals which have each of them their own energy epsilon k, but they're not coupled to each other. So this is the diagonal basis, which is uncoupled orbitals. Whereas this one is the real space basis, with coupled orbitals. So our diagonalization of the matrix T achieves the decoupling of these states. So you can see here that if I only have a single electron in the whole system, it must occupy one of these blue orbitals here, and the energy of the total system is just epsilon k for that particular site. So the obvious question now arises, what are the eigenstates and energies of the many-particle states? What about if I have some larger n? So what I have done is reduce the model to the free electron gas. I know what the eigenstates and eigenenergies of this system are in a trivial way if I'm only talking about a single particle in the electron gas. But what happens if I have a larger number of particles? For example, let's say I have 10 to the 23 sites in my system, and I have 10 to the 23 electrons. How do I construct such eigenstates, and how do I work out what the energies of those states are? So to understand this, the next discussion is going to be about the difference and the relation between single particle states and many particle states when we're talking about these non-interacting quadratic systems. The starting point will be to assume that we've already diagonalized our Hamiltonian so that it is already in the form of the free electron gas, the sum over k of single orbital energies epsilon k times the number operator for that orbital, which is fk dagger fk. And we have single particle eigenstates and what I mean by single particle eigenstates is they're eigenstates of the full Hamiltonian, but with the constraint that we have a single electron in the entire system. I'll denote these with this ket k as before, and that just means fk dagger acting on the vacuum. However, this vacuum is itself the vacuum of the full system with n orbitals, and it is something that lives in the Hilbert space H0. It's the Hilbert space with 0 electrons. The ket k, therefore, is something that lives in the Hilbert space with 1 electron. Which we call H1. And the n equals 1 condition means precisely that we sum up all of the number operators for all of the sites k, and the whole thing only contains 1 particle. So let's be clear. When we talk about, for example, the state k equals 1, what we mean by this is that there's 1 electron in the orbital k equals 1, and all of the other orbitals are empty. Let's talk then about the state k equals 2. In some obvious notation, that would mean that we have 1 particle in the second orbital, and likewise for k equals 3. So there's a single particle in the system, and it's located in orbital k. Now, remember that when I'm drawing out these kets here, this is already in the diagonalized basis. I'm not referring here to the occupation numbers of the original type binding model, but of the free electron gas after we've diagonalized it. So, bearing in mind the Pauli principle that tells us that any of these fermionic sites can have either 0 or 1 electrons, but not more than 1 electron, we can construct our many particle states from these single particle states. And we can do that with the following prescription. Imagine that we have some generalized state with n1 electrons in the first orbital, n2 electrons in the second orbital, n3 electrons in the third orbital, and so on, all the way up to n electrons in the capital Nth orbital. I can construct this from the direct sum over all of the orbitals k equals 1 to capital N of the occupation number of orbital k times the single particle state ket k. And this direct sum means that I can basically add up for each orbital the occupation numbers in here. But because we're talking about single particle states, this will either be 0 or 1. The sum of all of these numbers will either be 0 or 1. And I add up all of those for all of the single particle states in the system, but I multiply them by the occupation number nk. So if in here, let's say n3 is equal to 0, then in here, this n3 would be equal to 0, and I wouldn't get that particular single particle state contributing to the total sum. Now notice here that the direct sum does not just mean the regular superposition. These many particle states that I'm talking about here on the left-hand side, these are not a superposition of states. This direct sum means that for each of the orbitals that comprises the system, I just add up the contribution from each of these k states. So this is not a superposition. For example, in a two-orbital system, I could have a single particle state k equals 1, which would be 1, 0. I could have a single particle state k equals 2, which would be 0 and 1. And from these, I could construct the 1, 1 state by saying it would be 1, 0, direct sum with 0 and 1. And I'd add up each of those terms separately, and I get 1, 1. This is not a superposition of those terms. So how can we understand physically what these many particle states of the diagonalized electron gas look like? Well, let's imagine that we plot with energy increasing in the vertical axis. Let's imagine that we plot all of these single particle energy levels. These are the epsilon k's that appear in our diagonalized model. So let's start with the lowest single particle state, and then I have some other states in the system. There's some separation between them, however many states there are, just inventing something for the sake of illustration here. So I have a bunch of levels with increasing energy. There might even be some degeneracies in there, that's no problem. So the idea to work out the multiple particle states is just to sort of fill up these single particle levels, bearing in mind the Pauli principle that tells us we can't put more than one electron in each level. The ground state is the state with the lowest overall many particle energy. So how do we determine what the lowest many particle state actually is? Well, that actually depends on how many electrons we have in the system. So either we can specify a certain number of electrons and then say what's the lowest energy configuration consistent with that number of electrons, or we can imagine connecting our system to some kind of thermal reservoir. And that thermal reservoir will be characterized by a chemical potential, and this will set the Fermi level. And the Fermi level sets the maximum occupied single particle level at 0 temperature. At finite temperature, we have a distribution function which is precisely the Fermi Dirac distribution that we introduced in the last lecture. So, we either have a closed quantum system with a fixed particle number n, in which case we can talk about the ground state with a particular number of electrons, or we can think of an open quantum system in the grand canonical ensemble where we have a fluctuating particle number, and the particle number itself is determined by the chemical potential, and so the ground state is really the state of the system at 0 temperature. So how does this work? Well, for a given particle number, we imagine just filling up our single particle levels with electrons, starting from the bottom and working our way up. So let's say we had 6 electrons in the system. What I've described here would be the n equals 6 ground state. Because they're fermions, I can put in only one electron into each orbital. So if I had more electrons in the system, I could continue adding them into these levels. Notice that what I've drawn here is therefore the lowest energy configuration. If I were to promote any of these electrons into higher orbitals, it would have higher energy. Thinking about this in terms of the chemical potential, we would say that the Fermi level, EF, lies here between the highest occupied level and the lowest unoccupied level. So we imagine that we connect our system to a bath of electrons, and there is a sort of center of a zero of energy, which is the Fermi energy, and we imagine just sort of pouring in our electrons up to the Fermi energy, and they occupy these single particle levels up to the Fermi energy. And that's, of course, what happens at t equals 0. So what about excited states above the ground state? Well, we can generate these by considering the different ways of filling up our orbital levels. Imagine that we have our same set of levels before, and we add in our 6 electrons, but instead of adding the lowest energy configuration, I create an excited state, where this electron is in a higher energy state there. So this can be actually viewed as a particle-hole excitation to the ground state, because the previously occupied level is now unoccupied, so in the background of the ground states that looks like a hole rather than a particle, and then we have a previously unoccupied state that is now occupied, so against the background of the ground states that looks like a particle. So together this is an excitation where we promote a single electron from a previously filled to a previously empty state, and that looks like a particle-hole excitation. And I can imagine generating other excited states by making different combinations of particle-hole excitations or different superpositions of those. And what I've drawn here is still the excited states for the n equals 6 regime. However, I can also consider the n equals 5 electron sector. With Fermi energy located here, I can imagine filling up my system from the bottom with 5 electrons. And even though this is the lowest energy configuration for n equals 5 particles, it's actually still not the lowest energy configuration overall, because I could still lower my energy by adding in an extra electron to this final orbital, and that's the n equals 6 ground state that we talked about. So you can see that there's still an unoccupied level below the Fermi energy. So this is also an excited state. These excited states are not the ground state. They have energies that are lying above the ground state, but notwithstanding that, they might be thermally occupied at a finite temperature, and we can understand the probability distribution of a given state being occupied or unoccupied at a given temperature with a given chemical potential through the Fermi-Dirac distribution. We can imagine the ground state as being a filled Fermi sea of electrons, and any excitations into this Fermi sea would constitute holes or in the Fermi sea or particles above the Fermi sea. So these are excitons, bound states of an electron and a hole. The holes behave like positively charged fermionic particles against the background of the Fermi sea, and these behave like positrons. Obviously, these are not actual positronic particles in a microscopic sense, but these excitations behave as if they're positrons. These are quasi-particles of the system that have different properties from the microscopic constituents. The hole has a positive charge relative to the ground state. So this information is actually enough to understand now the amazing difference between metals and insulators. We can understand it from their single particle energy levels. Imagine the following two different scenarios. On the left-hand side, I see a bunch of single particle levels which are grouped into two regions. There's a low-lying set of energy levels, and then a gap, and then a higher-lying set of levels. So on the left-hand side, there's a gap. On the right-hand side, there is no gap. I've also drawn on the Fermi energy there, which is set by the chemical potential, and then we can understand what the ground state of such a system is. This is the T=0 state. We just fill up electrons in these single particle levels up to the Fermi energy. So that would be the T=0 ground state. What about on the right-hand side? Well, we again fill up the levels until we get to the Fermi energy with one electron in each single particle level. And again, this is the T=0 ground state. Now, the interesting difference between these two systems arises when we consider the excitations. The lowest lying excitation in this system on the left takes this electron and promotes it up here across this gap. And how do we do that? Well, we have to be at finite temperature. We could use the Fermi Dirac distribution to see what the probability of occupation of that excited orbital is. And what we see is that the occupation of this excited orbital is given by 1 over 1 plus e to the delta over kBt, where delta here is the gap size. So if the gap is large, for example of order electron volts, then we need an extremely high temperature, maybe many thousands of Kelvin, in order to overcome this energy gap and to thermally populate this upper band. On the other hand, if we look at the scenario on the right-hand side, the excited state there only involves promoting the electron a very small distance in energy, and therefore if there are low-lying excitations, you only need a very low temperature in order to excite them. This all becomes a lot more clear if we imagine going to the thermodynamic limit of n going to 10 to the 23 electrons, when we have 10 to the 23 different single particle levels, because then we form an effective continuum of levels, which basically form bands. Now we see in the continuum that we have these continuum bands of levels. On the left-hand side, we have two distinct bands with a gap between them. This one is called the valence band, and here we see that it is completely filled, whereas the conduction band is empty. And here I'm plotting the bands as a function, of course, of the density of states. On the right-hand side, I see a different situation because I only have one band, which is partially filled. And that means in the continuum, there is an infinitesimal energy gap between the ground states and excited states, and therefore at any finite temperature we can thermally populate those states. So ultimately we can understand therefore the scenario on the left is an insulator, and the situation on the right is a metal, because on the left we would have to go to very high temperatures to get the system to rearrange the electrons from the valence band to the conduction band, whereas on the right-hand side there are low energy ways to rearrange the electrons. If I were to apply, for example, an electric field to these systems, there would be low energy ways of rearranging the electrons in the metal, which could get the electrons to move around through the structure and therefore conduct electricity. On the left-hand side, there are no low energy ways to rearrange the electrons. I would have to apply an enormous electric field to rearrange the electrons to get them to move throughout the structure. So this is the key difference on the level of the tight binding models and single particle dynamics of why it is that metals and insulators have such different properties. Okay, so in the next lecture, we will look at how to solve tight binding models of periodic lattice systems, which model certain materials, by using the Fourier transform as an example of a kind of analytic canonical transformation. We'll see that this has the interpretation of transforming to momentum space, and the eigenstates will be so-called Bloch states, which are electrons moving in the periodic background potential of the lattice. So in this lecture, we looked at tight binding models and how to solve those models. We looked at two different ways of doing it, a kind of brute force method in which we formulated the many-particle Hamiltonian matrix and then diagonalized this by a basis transformation. And then we looked at a slightly more elegant way of doing things, where we do a canonical transformation of the operators to bring the Hamiltonian operator into diagonal form. And then from this, we have to do an additional step to construct the many-particle states and many-particle energies by filling up the single particle levels with up to the Fermi energy, or consistent with a certain number of electrons. And this gives us the interpretation of the ground state, which comprises the Fermi C, and excitations on top of the ground state. It also allowed us to understand the difference between metals and insulators in terms of whether or not the bands are empty, filled, or partially filled.